All right, sorry about the delay. Having some little internet issues, but we're good now. I'm gonna go ahead and share my screen. We're gonna start uh, chapter 5 today, and let me see. Yeah, I'm just waiting on it to share. This is gonna. I can tell you straight up. This is boring. This is gonna be boring because a lot of definitions and terms. But we need those definitions and terms to lay the foundation for what's coming. So just bear with me, and we'll get through it together. If it's boring, if you think it's boring, then it's double boring for me to teach it that way. But I have to do what we have to do. Um, so yeah, so chapter 5 is dealing with thermochemistry. So let's jump in right there. Come on. All right, so when we think about chemical reactions and we think about things reacting with one another, if we had some compound, hold up one second. We have some compound A going to B, right? If it's undergoing a chemical change, there's going to be some energy transformation, like some energy is going to get converted um, from one form to another, right? So all chemical changes, right? All chemical changes have this also experience changes in energy. Right. And when you think about a chemical change or a chemical reaction, let me just give you another term or a set of terms. Chemical reactions either give off energy or they absorb energy. So if it absorbs energy, right? If you have to add energy to the system to get the reaction to go, then we call that type of reaction endothermic. Let's call it endothermic reaction. If it releases energy, and we call that type of reaction exothermic. Right, so exothermic reaction. So endothermic and exothermic, we're going to learn a lot more about that later. But one of the things that is characteristic of exothermic reactions is that they're spontaneous, right? They don't require any additional energy to be added to the system. And endothermic is the opposite. It's non-spontaneous. You got to crank it up. You got to add a catalyst or you got to do something to get that reaction to do something, right? So when we talk about thermochemistry, that's simply the study of the amount of energy that's lost or absorbed when a chemical change happens, or even when a physical change happens. So energy loss or energy absorption. Over the course of a chemical change or a physical change. right? So what we're going to be talking about in this section is thermochemistry, how energy is studied, whether it be in the form of discussing heat capacity, whether it's in the form of discussing enthalpy, uh, Gibbs free energy. All of those are going to fall under this classification of thermochemistry. So now more definitions. What is energy? We hear, and I said this to the morning class, and I say it again, we hear that term thrown around a lot now. We always talk about the energy or the vibe or whatever, or someone has bad energy or good energy. But energy scientifically is simply uh, a capacity or an ability to either supply heat or do work, right? So let's define that by in scientific terms. So the capacity to supply heat or to do work. Right. And energy had you, I'm sure you heard this already as when you took your high school chemistry class. There's potential energy, and then there's kinetic energy. Right. This is associated with motion. This is associated with the position of something, some matter. Right. If you put a rock on the top of a hill, it has a lot of potential energy, but no kinetic energy. You push it and it starts rolling down the hill. It now has kinetic energy, but very little potential energy because the potential is dealing with its position, where it is in relation to some point B that it's trying to get to. But the kinetic energy is dealing with the motion of an object or the motion of matter. We're going to talk about that in terms of what it means for thermal energy, because that's the type of energy that we're going to spend some time discussing today. So we also need to define work, right? Work is a process of causing some matter, whatever it may be, to move against an opposing force. So let's define that too. All right, so it's the process of causing matter to move against an opposing force. So all these terms they all come full circle when we start applying them to thermal energy, right? And defining what thermal energy is, what heat is, what temperature is, all these things. So that's the next subtopic that we're going to discuss, right? Which is, I didn't put a date on here. It's today, the 8th. All right, so let's talk about these three topics. So thermal energy, temperature, because we got to distinguish between them, and heat. They're not the same. Even though heat is a function of thermal energy and temperature is a function of heat, they're not the same thing, right? All three of these are different. So when we think about thermal energy and we think about what that is, it's energy that's derived from the kinetic energy of atoms and molecules. So let's define that. was derived from kinetic energy, which is because of motion, right, of atoms and molecules. We've been talking about reactions, and let's say, for instance, we have, let's see, KBr, right? So let's say we have a reaction like this, and we balance that. We'll put a 2 here and a 2 here. Now to take care of the balancing part, right? But really what this is, if we write this out in ionic form, because this is molecular form, if we write it out like this, right? Right. So in order for that reaction to happen, right, these atoms or these ions have to collide and bump into each other at really, really, really high rates of speed in order for these reactions to happen, right? So that kinetic energy is derived from the motion of those atoms, in this case, or these ions. They have to, if it's in solution, if it's all aqueous, they're moving through solution and they're bumping into each other. And that's how the reactions are actually happening. And so when you think about it, like everything is moving. There's no such thing as something that's still. Even if it looks still, on the micro level, is moving. Like the atoms are vibrating, right, at all times. Even though we write stuff on paper and it's flat and it looks like it's nothing, like it's just, oh, it's just on paper. No, in reality, if you have a solution of KBr and it ionizes, those ions are flying around that solution like crazy. All right. Um, and so that the motion generates energy. And so that's what we mean by thermal energy. That's what we mean by that energy is derived from the kinetic energy of atoms and molecules, because atoms and molecules are always moving, right? And so another term that comes out of this, because as a result of that thermal energy, you can have both temperature and heat, right? So for temperature, let's define that. Right? It's when we think about temperature, it's just a quantitative measure, right, of how hot something is or how cold something is. I hate this word. Right. So the temperature is how hot or how cold something is. And when we think about hot and cold, those are functions of thermal energy, right? If something is hot, that means that it has high thermal energy. All right. Means that the atoms or the molecules that make up that hot thing, whether it's a rock that you put in a fire and it gets heated up because the atoms that make it up are vibrating faster than they normally would. Or if it's a chemical reaction like we were doing in lab when we did physical and chemical changes. I was on the stream when Jam was saying the temperature was increasing as the reaction took place, or the test tube got hot, or it didn't get hot, or it was just mildly warm versus very hot. So something that's hot has a lot of thermal energy. What that means is that the velocity, this one, let's see, high velocity. of your atoms and molecules is high. The faster they move, the more the thermal energy increases. The more the thermal energy increases, the more the temperature increases. And then we have something that's hot. Another thing that happens is expansion. Right? I asked the class this morning about how many of you have ever made collard greens? Anybody? By show of hands. Let's see, nobody. What about okay, one hand, Nazir? Okay, let me ask you something, Nazir. When those greens, because you know you got to cook if you put meat in them, you got to cook that first, so to cook off the bone, right? Got turkey, smoked turkey necks, ham hocks, whatever you're putting in there. But once you do that, when that water starts to boil, and you put the top on the pot, what do you observe once you seal that pot up? Do you ever pay attention to that? Like
You
when
talking about the steam on the lid?
steam on the lid, when it's really boiling, you can even see the top vibrating. Am I right?
Yeah.
That's because the gases are expanding. They heat up to the point where they need to escape, right? And so they even like that pot. Once you cover it, you can hear that top rattling. If you got a good rolling boil going, and that's because things that are hot tend to expand. On the flip side, if something is cold, right, the thermal energy is very low. That means that the atoms and molecules that make up that thing, whatever it is, are not moving very fast, right? So it's the opposite of something that's hot. So low thermal energy. Low velocity. And contraction. Right. And a way to think about that is, again, I'll use water as an example, right? When you freeze water, it contracts. The atoms or the molecules that make up the water come closer together. They contract. The motion slows down, and so that's what you see when water gets cold, right? If water is hot, it's going to expand. Eventually, it'll turn into a gas from a liquid. Uh, if when it gets cold, it's going to go from a liquid to a solid. And solids are characterized by the fact that the molecules are closer together. That's why solids are what they are. Um, and so when you think about temperature and thermal energy, they go together. Thermal energy is a result of molecular motion, kinetic energy, and the temperature is a function of that, because if the thermal energy is up, then so is the temperature. If the thermal energy is down, then the temperature is down as well. Right. So when we think about all of this, now we can introduce another term, heat. And let's say we have something that's hot and something that's cold, close to one another. That thing that's hot is going to release energy to the thing that's cold, right? And when that happens, that heat transfer right, is always from hot to cold. That's what heat is. Heat is the transfer of thermal energies between two bodies of different temperatures. So let's define that. Between two bodies with different temperatures. I used the example this morning, and I didn't think about the ramifications of it, but I'll use it again. Me being from Mobile, And going to Mardi Gras all my life growing up, I used to wonder why the crowds would stand how they would stand. Not just your neighborhood, because yeah, you're gonna stand with your neighborhood, whatever, wherever you choose. But it's just how we pack in. Normally, Mardi Gras in February. It's really cold in Mobile in February, so you go and you pack in. And honestly, that's a good thing because heat gets transferred from something that's hot to something that's cold. And some people have been, some of the people there have been, you know, they might have been had some hen, they might have been on some whatever. Uh, but your body, as it's processing that alcohol, it generates more heat in order to be able to process that alcohol. So if you're standing in a group like that, that heat gets transferred and someone with a lower temperature standing next to someone whose temperature is up, not with a fever, but I mean just, you know, giving off heat, that heat gets transferred. So that thermal energy gets transferred from, it can actually gets transferred from one person to another. Well, when I say bodies here, I'm not talking about human bodies. All right. So something that's hot is going to release heat. And then something that's cold is going to absorb heat. Right. So that's when we talk about heat, all heat is the transfer of thermal energy from one body to another, where one body has a higher temperature than the other. Right. Eventually, this thing is going to equilibrate and they'll both be at room temperature. Like they'll both eventually get to room temperature. That's called equilibration. So both bodies reach the same temperature. All right. But in general, heat is always transferred from high temperature to low temperature. All right. So now we know about thermal energy. We know about temperature, which is a measure of hot or cold, which is a function of thermal energy. And we know about what heat is, which is the transfer of thermal energy from one body to another, where one body is hotter than the other. All right. Um, so now we need to ask this question. We need to ask, how do we measure energy? Because we can measure temperature, but temperature doesn't necessarily tell us how much energy is there, right? Temperature can tell us if something is high energy or low energy based on whether it's a high temperature or low temperature. But we can't tell how much because we need units. We need specific units to measure energy, right? Because we say energy is the capacity to give off heat or do work. So energy can cause temperature change, but that's not how we measure it. So how do we measure energy? And we're going to have two terms for that.
Is it in joules?
Yes, that's one of the terms. That's good. You're exactly right. One of the terms is joules. And the units for joules, kilograms per, hold up, kilograms times meters per second square. All right, that's one of our energy terms. All right, and then what a joule is the energy required to the energy required when a force of 1 Newton moves an object 1 meter. Right, that's how you define that. or force of 1 Newton. That's that. And that's why this is what it is, right? Kilograms is mass and meters per second squared is acceleration. So that those two terms together are a unit for force. So this is mass. This is acceleration. And then together, right? That's force, because force is mass times acceleration. So it's the energy required when a force, excuse me, of 1 Newton moves an object 1 meter. Let me that so you know it's not a part of that. Right. So joules, that's the more consistent way of measuring energy. The other term that we use to measure energy is a calorie. Or calories, right? And for calories, it's a little bit inconsistent, even though we still use it. We can interchange between joules and calories pretty easily. If I'm not mistaken, the conversion is 1 calorie is 4.184 joules. That's the conversion. So you can convert between them, but calories is has a little bit of a factor of pressure, and also it's affected by atmospheric pressure, and so that's why it's a little bit less consistent than joules. So that's why joules is the SI unit for energy. So this is SI unit. Right, but a calorie is in similar fashion to a joule is the amount of energy required to raise 1 gram of water by the temperature of 1 gram of water by 1 degree Celsius or 1 Kelvin. And you know that temperature is pressure dependent, right? So the temperature that it might take in Colorado for water to boil or for water to increase in temperature, it might be different than the temperature in Alabama because of that relationship between temperature and pressure. All right. So this is a calorie is the energy required to raise 1 gram, raise the temperature of 1 gram of water by 1 degree Celsius or 1 Kelvin. And remember, for Kelvin and degrees Celsius, the relationship is 273. Right? So 1 Kelvin equals whatever that degree Celsius is plus 273. I'll just say Kelvin. So Kelvin is the degree Celsius plus 273, right? So we have a lot of definitions. We know terms to describe energy now. We know what heat is. We know what temperature is. We know what thermal energy is. We know what energy is, what work is. And so now how do we apply this? Since we're studying thermochemistry, how do we apply this to some thermochemical phenomena? Well, first thing we're going to look at is specific heat, and then specific heat capacity and heat capacity. So this is the application. We're going to apply to heat flow and temperature change. Right. So one term that we can apply this to is a term that we'll call heat capacity. It's uppercase C, and that is equivalent to Q over delta T. Right. So C is heat capacity. Q is the quantity of heat, which is measured in joules. Right, so that's in joule. And then delta T is temperature. Right, this is the final temp. And then this is the initial temp. Right, so it's just that delta is just a symbol for change. Right, anytime you see that in front of a term, it's just a change. Right, so delta T is the temperature change, final minus initial. Q is the quantity of heat, and then C, uppercase C, is the heat capacity. This is an extensive property. Anybody remember what that term means? Right, it just means that it depends on the amount of a substance. Like mass is extensive, right? Because if you have a handful of let's say marbles, and you have a basket full of marbles, the basket is going to have a greater mass than the handful because there are more marbles in the basket. So extensive properties are based on the amount. Intensive properties are not, right? They're not based on any amount. They're just based on the actual substance itself. All right. So what is specific heat? Right? It's exactly what the relationship says right here. It's the quantity of heat absorbed, or received when it undergoes a change in temperature, when matter undergoes a change in temperature. So that's the Q. Right? When matter undergoes a temperature change. So it's how much heat is either absorbed or released when matter undergoes a temperature change by 1 degree Celsius or 1 Kelvin. That's what heat capacity is. And it is dependent on the amount of that substance. All right. There's another term that is intensive and not dependent on the amount of a substance, and that is the specific heat capacity. So let's talk about that. That's a new page right there. So this is heat capacity. Well, now let's talk about specific heat capacity. Right, and that's a lowercase c. And it's Q. It's the same setup. The only difference is the mass is involved. And the mass is going to ensure that the specific heat capacity is specific to whatever the substance is, and it doesn't change, right, with the amount. So it's always going to be the same. That's why it's called specific heat capacity, right? So it's the same thing. It's the quantity of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So raise the temperature of 1 gram of a substance by 1 degree Celsius or 1 Kelvin. All right. And so now we have a way, and this is, again, this is intensive. It's irrespective of the amount. Right. It also happens to be a ratio of two extensive properties. Right. So the energy here as well as the mass, both are extensive. So they depend on the amount. So because of that, if you recall from way back when we first started talking about matter and states of matter and properties of matter, anytime you take the ratio of two extensive properties, then that gives you an intensive property. Kind of like when we talked about density, we talked about mass, we talked about all those different things. Like density is intensive because it's mass over volume, where volume is extensive because it depends on the amount, just like mass depends on the amount. All right. So let's think about this in terms of, like we always do, how do you manipulate these things? Because you're always going to have to manipulate these types of equations because you're not always going to be given straightforward data. Sometimes you might have, if you got 3 terms or 4 terms and you need to find you're given 3 and you need to find the 4th one, then it's going to call for some manipulation. Right. So right, if big C is Q over delta T, then we can solve for, if we got any 2 of those terms, we can solve for the 3rd one. Right. We know that we can say C times delta T is Q. Right. Or we can say Q over C is delta T. We can find any one of those terms. If we know 2, we can solve for the 3rd. And that goes for any equation. If you know any of the variables, if you know all of them except 1, you can solve for that 1. Right. Same thing with specific heat. So this is heat capacity. And then how do I manipulate specific heat capacity? Right, which is lowercase c is Q over M times delta T, where M is mass, delta T is change in temperature, Q is the energy or the heat quantity. Right, so now I got 4 terms, right, where this is heat, this is mass, this is temperature change. Right, how do I manipulate that? Well, I can say C times M times delta T equals Q. That's one thing I know for a fact. I can say that Q over C times delta T, I can get the mass, right? I can say Q over C times M, and I can get the temperature change. Anything I want, I can find. As long as I know 3 of those 4 terms, I can solve for the other one. Right. So this is important because, again, some of the problems you're going to have to solve involve manipulating this relationship. And as long as you know how to do that, you won't ever like be lost as far as like how to find a particular term. So let's do, before we quit, let's do an example. Right. So I have a flask with 800 grams of water. Right. So that's my mass of my substance is water. That's the mass. The temperature changes. TF is 85. TI is 21 degrees Celsius. So now I can figure out delta T. It's 85 minus 21. That's 64 degrees Celsius. Right? And the question is, what is Q? Right? The good thing is many of the specific heat capacity values are already known, right? For water, this is specific heat capacity. It's 4.184, and this is the unit, joules per grams degrees Celsius. That's very important because anytime you do a calculation with a number that involves multiple units, you need to be able to cancel out those units, right? So if you recall the equation, it is Q over M times delta T is C, and I want to find Q. Right, so I'm going to say Q equals C times M times delta T, and I know every one of those numbers, right? Notice here what when I solve this, let's put the numbers in. So this is 4.184 joules per gram degrees Celsius. All right. And M is 800 grams. And then the delta T is 64 degrees Celsius. Now notice all of my units. This is important because this is a stumbling block. A lot of times it's forgetting the units. So you got degrees Celsius and grams here. You got degrees Celsius and grams here. And if I write that out, it looks like this: joules over grams times degrees Celsius. Right? So the grams are going to cancel. The degrees Celsius are going to cancel. So the units for Q are joules. So that's measured in joules. So can somebody give me that calculation real quick? 800 times 4.184 times 64. What do you got?
I got 214,220.8.
Okay, so 214. You said
220.
So let's say
0.8.
214,221 joules. All right. Normally, we'd write this in scientific notation. So we'll say 2.14 times 10 to the 4th joules is Q. All right. So that's how much energy it takes to heat up water, 800 grams of water, from 21 degrees to 85 degrees Celsius. It takes 2.14 times 10 to the 4th. That's a lot of energy. 10 to the 4th joules, or 21 kilojoules. All right, so we're out of time. I got one more example, but I'll wait. We can do it on Monday, God willing. So we're gonna stop here, and we'll be back on Monday, God wills, and y'all have a safe weekend and a good weekend. Come back in one piece. We're in the home stretch. We are in the home stretch. I don't know if you feel it, but I feel it. Okay, let me answer your question, Mary, about specific heat capacity. The difference in that and heat capacity is that this is a intensive property. So it's the amount of heat necessary to change the temperature of 1 gram of a substance by 1 degree Celsius or 1 Kelvin. So with specific heat, with heat capacity, not specific, but just heat capacity, the mass is not involved. It's just heat divided by a change in temperature. So that's the difference.
Okay, that makes sense. Thank you.
Great question, by the way. I'm sorry I didn't see it sooner. All right. Any other questions about anything? All right. We stop.